So here we have some data, some development economic data about the gross national income per capita, which is on the y-axis, and the adult literacy rate on the x-axis. And we'll talk about how we can use transformations to better understand this data and better model this data. So the first question is so here's actually, before I get into that, here we are basically converting the log of the y-axis to generate this plot over here. And this is again the log gross national income per capita. And you'll see that this data, which used to be of this kind of shape, is now much more linear with respect to the axes. So this is what transformations help us. Linear things are more easy to model and can also help us understand how one feature might affect the other in much more intuitive way. And we'll be talking about linear regression in a few lectures. So let's talk about the first part. The first part is asking, instead of using the log 10 transformation, what other transformation can we use? So let's look at the Tukey-Musteller-Buzz diagram. And here we see that we only want to use either these or these. So these are these. And basically it's either square root of y or log y, or if you want to make a transformation of x, you can do x squared or x cubed. So keeping that in mind, let's go one by one. So we can do log of y, because here e is just a different base for the logarithm. Now the base now you just choose the base depending on the skewness of the data set, but I don't think 10 and e should be much different. Then you can't do 10 to the y, you can't do square root of x. You can do x squared, as it's one of the options as represented in this diagram, and you cannot square y. Okay, so that was part A. Let's talk about part B. So part B is asking that C and K be some constant values, and X be the literacy rate, and Y be the gross national income. Based on the plots, which is the best way to describe the pattern? So first of all, what is the pattern that we are seeing in the data set? We are seeing that there's a linear relationship between the log of y and the x variable. And how do we model that? So let's start with that assumption. So all we're saying, first of all, is that log 10 of y is equal to some constant times x plus b, where this is the slope and this is the y-intercept. And we can process this further to obtain an expression for y itself. So we can raise both sides to the power 10. So this will be log y is 10, and 10 to the kx plus b. Y will be equal to 10 to the kx. 10 to the k. So the left hand side just evaluates to y, because 10 to the log of something base 10 gives you the same thing that is in the log. And you can separate these 10s on the right hand side and write it again differently. So here you can write this down differently. And you could think of this as some constant c, and you could think of, and this is, I guess, one of the options. So here, basically, the correct answer would be B, because 10 to the B is just a constant, and 10 to the kx is, again, matching this pattern over here. Okay, so again, it's very important to understand what the real relationship is between the real variables. The log of something is a variable which doesn't have that much physical meaning, but really finding the meaning of the real variable gives us an insight into our data. Okay, so moving on to part C. Which parts of the plots could you use to make initial guesses on C and K? Now, if you're familiar with how these plots, how linear plots work, you can just say that so the y-intercept and the slope can help you get C and K. Specifically for C, the slope, C is equal to 10 to the B, and B was the y-intercept of the trend line that we had over here. So this when this reaches 0 at some value, that value will be the y-intercept. This will be B. Okay, so B, C is equal to 10 to B, and B is y-intercept of the trend line and what for K is just directly the slope as we saw in our math. So K is just the slope directly of trend line. And all of these trend lines are for the transformed plot. Okay. So here, let's see what part D is asking. Part D is where Shani's friend Yash says that since this line is going up and to the right, we can say that in general, the higher the literacy rate, the greater the GNI per capita. Is that a reasonable interpretation of the plot? Yes. And that is because, as Yash rightly pointed out, the trend line is indicating that the trend of this data is increasing. The GNI is increasing with increasing literacy rate. However, this is just correlation. And not causation. So again, keep that in mind, that we don't know there's a causal relationship, but we can say that there is some kind of relationship which is increasing. I just pointed out. Okay, so part E is a very interesting question actually, and this requires a lot of deep thought. So again, I would recommend you to really think about what you would do, but I'm going to go over it. So here, sometimes our data could contain 0 or negative values, and we know that for a log plot. So if you try to visualize the log plot, so this is log of x, and essentially at 0 it goes to negative infinity, and there is no log. You can't take a log of a negative number. So what do you do then? So one such approach that we have as a soft solution is that, let's say we have some negative data. So let's say this is -2, -0.5, and 1. This is like you could think of this as the number line. We could change our scale such that the lowest possible number has a value of 1. So if -2 goes to 1, -0.5 will have to go to 2.5 because it's 1.5 points ahead of -2. And similarly, the 1 would become a 4. Now, again, we do this so that we can make everything positive. If it's any number between 0 and 1, as you can see, it can be this curve is very steep, and the value can be really negative. It can really skew our data. However, when we have these positive values, the values are in a much reasonable range. The log values are in a much reasonable range. So this transformation can help. So this transformation before the log transformation can help us use the log transformation effectively. Okay, so that's the end of this worksheet. And as usual, if you have any feedback, feel free to give it in the weekly surveys. And yeah, I'll see you next week. So here, so in question 2, we'll be talking about the professors wanted to survey the students on the exam's difficulty and use the mean of the students' responses as the estimate. So the first part asks us what is the population that the professors are trying to understand? Is it A, B, C, or D? So again, as usual, take a moment to think about this before I go over it. But I'm gonna go ahead. So instead of me giving you the right answer, I'm just gonna go over all the parts one by one. So here, since you're trying to estimate the exam's difficulty, students in the 100 might not be a great option because some students might be missing the midterm. Some people might have taken incompletes, or they might be missing due to health reasons or any other reasons. So A is not the right answer because not all students take the midterms, although it is uh, more or less mostly all students take it. Um, and for the same reasons, actually, A, B, and C are wrong. Sometimes, again, students might be enrolled in the ed, but they don't have to take the midterm. And students who attend the data lectures don't even have to be enrolled in the class. So C is wrong. And since we're trying to estimate the exam's difficulty, so the people who actually took the exam would be the best people to answer that question. Therefore, D is the absolutely correct answer in this scenario, making the least amount of assumptions. Okay, so B is a very interesting question. Here you are given a few different methods for collecting the survey data about the midterm, and you're asked which of these following is the best. So again, there's some deficiencies in all of these methods, and we could talk about them, but you have to be able to select the best method possible in order to minimize bias and also be more uh, have maximal responses. Okay, so I'm going to go over it one by one. So let's talk about part A. Part A is about professors adding a slider poll and only considering synchronous responses. So this is, I guess there's two reasons why this might fail. So first of all, there's multiple groups of students so there's different groups, right? So certain students attend lecture and the other students just do the asynchronous survey. So if we only consider synchronous responses, we'll only be sampling people who attend lectures, and this will introduce something called selection bias into our sample. And we will make generalizations for the entire class based on a certain group. Since you don't want to do that, A is not the best method for this question. Also, not all students fill out the lecture participation. So even if you consider asynchronous, this might still not be the best method. But again, that's a deficiency that is hard to overcome. Let's talk about part B. So part B is where you add a question to the homework assignments of a simple random sample of students within every discussion section. So I like this one for multiple reasons. So first of all, students, every discussion TA has a different teaching style, and students can really, and that can actually result in students performing differently. So if you make a simple random sample of students across all discussion sections, and you can minimize that bias and make a generalization across the entire class. So, and again, homework is something that everyone does for the most part, since there's no drops. So B seems like a good way to sample. Again, students might not do the homework assignments. This semester, we don't have students. Some students are not taking discussion, not in the discussion section, so this might not work out. So there are limitations, but it still seems to be a valid method. So I'm going to place a tick mark here. So in part C, professors are making a post on Ed to submit a Google form containing the survey question. So here, you should keep in mind that not everyone looks at Ed. And even if you look at Ed, you might not go through the extra friction to submit a Google form, which contains survey question. So there's a lot of friction involved in this, and it's hard. And it's hard to control that. Also, again, students who might look at that might be a different group of students than those who don't. So that can introduce selection bias into a sample. So that removes part C as an option. And then part D is where professors actually go to a simple random sample discussion sections um, and ask students in the group about what they think. So while this makes sense and there's a lot of randomness involved, you're going to discussion sections. The problem is that they might not get an accurate measure of the exam's difficulty because of social pressure. When students are asked in groups, they might bias the results of the survey by not speaking their mind. Um, so in that case, D also might not be the best way to sample for the survey. Okay, so that's the probability and sampling portion of the worksheet. And yeah, I'll be back for the simple linear regression part. So let's talk about some simple linear regression. So here we have Nile Red doing some experiments. And here is the plot that that Nile Red made these experiments. So you have the yield of grape soda on the y-axis, and you have the temperature on the x-axis in Fahrenheit, and you are asked to calculate the slope and the y-intercept of the line of best fit using mean squared error as our loss function. So we hope that this is a very gentle introduction to the idea of simple linear regression. So if you went through the slides in lecture, you might have noticed that to calculate these parameters, that's actually just, for simple linear regression, there's a set formula that you can use. So to calculate the slope, which is theta 1, what you can do is you can just use r times sigma y over sigma x. And all this information is given to you in this table over here. And for theta 0, it's y bar minus theta 1 hat x bar. So let me briefly talk about what each of these terms are, and then we can go forward. So sigma x is the standard deviation of the values in x. Sigma y is the standard deviation of values in y. R is the correlation coefficient. It basically talks about how correlated these values are. Like, for example, how an increase in one value would affect, how a change in one value would affect the other value. X bar is the mean of all the x values, and y bar is the mean of all the y values. Okay, so keeping that in mind, let's do some calculations. So R is just 0.5 and 0.3 over 15. And this turns out to be 0.01 very nicely. So y bar is 3 and 0.1 times 75. So this is 2.25. So essentially, I'm just going to write this in a different color. Y is equal to 2.25 plus 0.01x. Okay, so that's your line of best fit. Okay, so you're also asked to plot the line on the graph above. So what you can do is, so the easiest method that I think you can do is, given an x value, just make 2 points. Like, given two x values, make 2 points and just connect them because it's a line. So let's say x is equal to 100. So when x is equal to 100, based on this line of best fit, this will be 3.25. So let's do that. So let's make a point around 3.25 or 100. Roughly speaking, that red point will go there. And then you can also do the same for 50, in which case it will be 2.75. So let's say somewhere here. And then you'll just connect them. Okay, so that should be your line of best fit. Okay. Yeah. Let's go to part B. In part B, you have this plot of residuals. So residuals is where you do observed y minus predicted y, and your predicted y is again coming from the line of best fit. Um, so here you have the residuals against the temperature, which is the parameter that you're varying, and you were asked about what this plot reveals to you about the relationship between x and y. Uh, so what you should really be looking for is whether the points are randomly located around the residual, like around zero, or do you see some kind of pattern? And at least in this case, what you should notice is that there is some kind of pattern. They're not randomly distributed. It does seem to follow some kind of quadratic curve, which I'm going to talk about in the next part actually. But that's something that you should think of. So since it's not equally random, if random would just be like equally spread out in all across all values, but that's not the case. So um, in this case, since there's heteroscedasticity in our residuals, the relationship is likely to be not linear. Um, so let me just put that down. Relationship between x and y is likely to be non-linear. So that means that we need more features, which is a term which you'll get more familiar with over the course. But you need more sort of features to um, um, better model this scenario. So let's talk about that actually in the next part. Um, so here you're asked about which of these following relationships most closely represent the relationship we see. And here, if you actually go to the residual plot or the original plot, you'll see that there is some kind of quadratic nature, like whether there's a dip and there's a bump back up. So what you can do is actually, let me pause this a second. Sorry, my iPad was slow. So let me start again. So in part C, we are asking which of these relations most closely represent the relationship. So in this case, again, both the residual plots and the original plot, you see this kind of curvature, and this is inherent to the quadratic form. So let's only consider the quadratic options over here, which is A or B. These two can be ruled out. So within these two, what do you think should be the case? So if we actually go back to the original plot, you'll see that the points are trending back up. Sorry, the points are actually trending back up as for lower values. So by the time you reach 0 Fahrenheit, you should still be at a positive value for the y. Your y-intercept should be a positive value and probably higher than 3 or 3.4. So given that your y-intercept is not 0. So if it's not 0, then A can be ruled out as well. So actually, let me write that down. A can be ruled out as well, and B will be the correct answer. So you could think of this extra term as a feature. You're thinking that maybe, and this is the nonlinear term that makes this relationship possible. So you could think of this as an extra parameter that you think can be used to model this relationship. So that's it for today, but I just hope that this was a very gentle introduction to simple linear regression. We'll be doing much more complicated stuff in future discussions, and this will kind of like lay the foundation for that. So again, that's it for this week, and I'll see you next week.